Good afternoon, TechNation. Welcome to another fantastic Webinar Wednesday. We are excited to have over 400 pre-registered attendees for this webinar. Today's presentation is eligible for 0.1 CE credits from the ACI. Let's get started by giving away one lucky attendee a TechNation Tour t-shirt. Our 8th annual TechNation Reader VIP party will be held at the AMI Conference on Sunday, June 5th. What Tampa Bay hockey team might be playing in the Stanley Cup playoffs that night? Answer now using the questions feature on your dashboard, and you can RSVP for that TechNation Reader VIP party at onetechnation.com/AAMI. While you're answering, TechNation would like to thank our sponsor today, Technical Prospects. Technical Prospects is your only alternative to new, pre-owned, and refurbished Siemens medical imaging parts, also offering engineer training on your Siemens medical imaging equipment and technical support on your parts purchases. Technical Prospects is your partner at every stage. Visit them at www.technicalprospects.com to learn more. Okay, it looks like we got a winner here, Mike Morgan. Mike Morgan correctly answered. The Tampa Bay Lightning could be there in the Cup playoffs during the AMI show. All right, let's get started. Our presenter today is John DePasquale, technical trainer for Technical Prospects LLC. John is a certified biomedical equipment technician and has over 25 years experience in the HTM industry. John, you can begin whenever you are ready.
Good afternoon, TechNation, and welcome to Image Quality and the Imaging Chain, a Service Perspective. Before we get started into the material, a little bit about my background. I got my start in the U.S. Air Force, initially as an aircraft electrician, where I spent 4 years doing that, and my last 18 years as a biomedical equipment technician. There I worked as both a technician, a manager, an instructor, and also in my final tour as a regional manager in charge of the Western region. After military service, I went back out into the industry, and I worked in various imaging and biomedical capacities, including asset management for both in-house and third-party contract positions. In early 2000, I left the industry and was teaching high school mathematics in Connecticut, so I can truly appreciate what your kids' teachers go through. After 7 years of that, it was time for me to come back. And I came back and I hooked up with an OEM called Hologic, which was my first OEM experience. During my time there, in addition to technical support, I became their technical trainer on analog and digital imaging systems and their support systems for their mammography lines. In 2013, early in the year, I moved to Wisconsin, and later in that year, I hooked up with Technical Prospects and began my career here. My background includes a master's degree in education from Boston University, a bachelor's in electronics engineering and business administration from Wayland Baptist, 2 associate degrees from the Community College of the Air Force in both instructor technologies and biomedical equipment technologies. As John said, I've been a CBET since 1994, and while in the Air Force, I obtained their master instructor rating. But you're not here to talk about me. You're here to hear about image quality and the imaging chain. So let's get started there. What we're going to look at here from a service perspective is image quality, the imaging chain components, service tests that affect the imaging chain, and lastly, a little bit of preventive maintenance. So let's get started right in real quick with image quality. Here we're going to check out determinants, sharpness, contrast, blurring, and radiographic noise. All of this information on image quality can be quickly summed up here on this chart that we see here in front of you. I'm going to be breaking down this chart as we go through this and discussing all the individual factors here as we go through it. So moving on here into our determinant screen, we have 2 primary factors. The first one is radiographic sharpness, and the second one is radiographic noise. In breaking this down, we're going to look at, under radiographic sharpness, both contrast and blurring. And under radiographic noise, further define this under the influences, radiographic model, and lastly, artifacts. Starting with contrast, this is a term that we need to understand. Contrast basically is something that is black and white. That's a very high contrast. However, it is also relative in nature because low contrast is black on one end, white on the other, and varying shades of gray in between the two, depending on the number This would, again, determine the amount of contrast. As with this here, our technicians use this word in terms of subject contrast. When they're talking subject contrast, they refer to the ability of the person viewing the radiograph to be able to discern between adjacent parts in the image. There's a lot of things that affect subject contrast, but we're going to start with absorption differences. First one we're going to talk about is that of thickness, and this is pretty obvious. The thicker the object, the harder it is for the X-rays to go through, therefore we will be able to see differences on the radiograph. When we look at density here, now we're talking mass of the object. And if we look at this, just in terms of our body, we have different densities. Addressing two cavities, for example, the abdominal cavity and the chest cavity, these are two different areas of our body of different densities. The abdominal cavity is actually the more dense of the two, because even though our chest cavity may be wider in width, there's this huge air pocket in between which has no density. Now, this is important for the technologists because they need to take advantage of the anode heel effect, where we actually have a stronger X-ray beam on the cathode side of the tube in doing patient positioning in order to ensure a good subject contrast for what they're trying to see in the radiograph. The other part of subject contrast that we're going to deal with is atomic number. This here talks about the different elements in our life. Probably most of you has never thought about thinking about that periodic table that you studied back in your high school physics or chemistry classes. Well, when we look at the atomic number, we're looking at the atomic number of subject structures in our body. We're looking at fatty tissue versus muscle tissue and things of this nature. Because they have different absorption rates and because they're comprised of different materials, it will affect how they absorb the beam. Another application of atomic number for us is lead and lead equivalents. As you all know, our X-ray rooms are lead lined to prevent radiation from going through our walls and exposing passerbys. We can also use something called lead equivalents. If I were to use aluminum, I would have to put a number of sheets of aluminum just to get the same absorption qualities as that thin piece of lead. Hence the application of atomic number. At radiation quality, one of the things that we're looking at here is the actual target itself. Most of radiology today uses a tungsten target. However, in the modality of mammography, they initially started out with the molybdenum target and more recently have advanced back to tungsten. Now, this type of material is important because it creates a different quality of radiation that's coming out of the tube. In some cases, we need to be aware of this because if we replace the wrong tube on a piece of equipment, that will create serious issues. But there's also manufacturers out there that will have a tube with both of the types of materials in target. So again, we have to be very careful when we look at this and replace our tubes appropriately. When we look at KV, which is the Q factor of quality for radiation, we need to recognize that KV is not homogeneous. That is, not all the photons are created equal. They are of different frequency and wavelength, and they have an inverse relationship. So keeping that in mind, we have different factors and different strengths in our X-rays as we go through. Filtration is another thing that we are using, and filtration is basically broken down into two areas, both inherent and added. When we talk inherent filtration, this is just what's built into the tube. There's nothing we can do about it. It's just something that exists that we have to compensate for. However, added filtration is used to shape the beam in order to create better quality radiographs. An example of this would be taking an X-ray of your foot, which has both from the toe to the ankle. Obviously, there is a distinct difference in thickness between the ankle and the front of your toe. If I were to use a wedge filter to more uniformly set this up, I would put the thin edge of the filter over the ankle and the thick end over the toe, effectively creating a square and a more uniform overall thickness for my radiograph. Another factor that affects subject contrast is scatter radiation. Now, scatter radiation is anything that radiation basically interacts with in the beam. However, the primary object of our source of scatter radiation is the object we are examining in itself. How we reduce this is by controlling the beam through beam limiting devices. We restrict the area, thereby minimizing scatter radiation. We can do compression to reduce area. Air gaps are also used to allow scatter radiation, which is radiation traveling not in straight lines but off to the sides, allowing it to escape. If you think of your back on a table, it does not lie flat. That space is the air gap. It's also the air gap from your body to the actual space where the imaging receptor is, such as a piece of film or the cassette. That air gap also allows scatter radiation to escape. However, the most important thing that we use to reduce scatter radiation is that of a grid that is in the beam. Receptor contrast is something we also need to address that will affect radiographic sharpness. Looking at this from a screen film perspective, processing is the single biggest thing that will screw up a radiograph. You can be the best technician in the world, take a great picture, but if the film processor isn't properly set, you're not going to get a good quality image. Now, things that we have to consider in processing, back in the days of wet film, was chemistry temperature, chemistry strength. Is it agitated and having the particles at the strength of the chemical more uniform throughout the entire area? And the time spent in each phase. Another factor that affected screen film processing was something called density fog. Now, this is where film gets fogged unintended by us shooting the X-ray. This can be caused by light leaks where you have a very dark edge. It can be from prolonged exposure to safe lights. And you're saying, wait a minute, safe lights are supposed to be safe. Yes, that is of the red frequency. However, if it's too long, even though our film normally responds to blue and green frequencies, it will in fact damage our film and create a light fog, which will affect the overall quality of our radiograph. Another factor that will affect us is chemical fumes. Prolonged exposure to this in that darkroom environment is something that we need to be aware of, particularly when the film is out of the storage area. Moving on from here, because we don't use film that much anymore, we are more into the CR world. Here we have to worry about the appropriate S-curve. Are we delivering the appropriate S-curve, which is radiation necessary for the CR cassette processor to properly process the image? The other thing, because these cassettes are used on a reoccurring basis, are we properly flash clearing it? Get the appropriate amount of white light to flash clear this, we're going to have a fogged image remaining on the plate, so that when we add the next image, we are fogging our image. Moving into the digital world, this is also very similar in this regard, because in our digital world we have to flash the entire array or transistors or whatever we're using for that particular type of detector in order to create a balanced white light, so that when the new image comes in, we have a good quality image. When we move on and look at blurring here, one of the things we like to talk about here is motion. If, for those of you who remember the days of single lens reflex cameras, you remember there was plenty of different type of film speeds that you could buy, anywhere from 100 to 2,000 speed. This all related to how much light was necessary to properly expose the film in order to create the picture. Radiographic film is very similar in nature when it comes to this. We have different film speeds. The whole purpose of all of this here is to prevent movement. All right? Resolution is movement. Have you ever wondered why the radiologist says just before your X-ray, take a deep breath and hold? beep, breathe. She wants no movement on the radiograph. Moving on from here, we have geometric blurring. When we take x-rays, our x-ray tube needs to be at a perfect 90-degree perpendicular angle to our imaging device, whether it's film, a detector, or whatever we use. If either of these, either the x-ray tube or the receptor is at a slight angle, we will create distortion based on a geometric distortion of our object. Another part that we need to look at here is an acronym called ID, which is called source to image distance. Part of this source to image distance, we have two distinct breakdowns. One is SOD, which is source to object, and the other is OID, which is object to image distance. These have an inverse relationship. The key here is the object to image distance. The greater the object to image distance, the greater the magnification, the greater our image will also become distorted. Another factor that we're looking at here as part of the geometry of making the X-ray is the focal spot size. Our X-ray tubes have two distinct focal spots, a large and a small, and based on the type of tube ordered, we'll have different sizes. Generally speaking, it is stated that the small is used for detail. What they're talking about here is how we impact the edge lines of the object that we're trying to see. The smaller filament will give us less distortion, hence the term detail for the small filament, where we use the large for higher energy shots, and even though there is some distortion, it's considered acceptable in order to create the overall X-ray. Other factors of blurring that come into play are light diffusion. Now, we use light in both film and CR. When we're using light, we use a phosphor here to change the X-ray energy to light energy. This is all going to be determined by the thickness of the phosphor, the particle sizes used, and the types of dye that make up this overall structure of light conversion here for us. The other factor that comes into play here is screen contact. As we look at screen contact, the tighter the contact of the screen to the film, the less distortion. If there's gaps or bubbles, what we have then is the light being able to travel other than in straight lines, again, reducing the sharpness of our image. Moving on from sharpness now, let's take a look at radiographic noise. We're going to start here initially with the influences, and the first influence we're going to talk about is that of radiographic model. Now, model has a definition of mark with spots or patches. And if you think about this, this is exactly what we're doing. In today's digital world, we have a scintillation layer that converts the X-rays to light, and we have pixels. Those are individual spots that we turn. Back in the film world, we had particles in the screen that glowed to create the light that was exciting silver halide crystals on the film. Again, it's the same type of thing. We are marking the X-ray with spots or patches. When we look at this here, we break model down into three distinct areas, first being structure. This refers to the non-uniformities in screen construction with a minimal, and today there's a minimal effect in today's world, mainly because of the fact that we are using man-made crystals. Moving on from this, we look at quantum model. This exists real heavily today and is one of our bigger influences in radiographic noise. Here we're talking about the differences in the number of X-ray photons in each square millimeter of film or the detector. Now, we already know earlier in our discussion that X-rays weren't created equally in terms of strength. Now we're saying that there's not the same amount of photons over each square millimeter of film. Again, this is going to create noise in different degrees of visibility for us. Our third form of model is the receptor itself. All right? Back in the days of film, this was the amount of silver halide crystals. Were they all the same? Are they the same size? All the different factors that exist back in the days of the receptor. Today, we look at pixels. If you think back just in our cameras themselves in today's day and age, I remember back my first digital camera was a 1.3 megapixel Sony Mavica. Today, I run around with a 16 megapixel Sony camera. All right, more pixels, better quality, better image. Going into our next factor here, we talk about the screen film factors of radiographic noise. And again, some of this applies to CR, but we can take this imaging information from the days of screen film and apply it today to the digital world. We're looking at the absorption of the X-ray beams, the screen factors, how much light we're putting out during the transfer of the X-ray to the light, the diffusion of the light. Are we getting a good transfer? Are we lighting the appropriate areas of our imaging device? The speed of the film. Are we getting the good transfer? Are we getting the appropriate optical density that we need to see? And lastly, is our film responding in terms of creating the contrast that we need to see in order to determine a good quality radiograph? Helping that also is the quality of the irradiation. And this is because we can use different KVs for different exams based on the body structures that we are in fact imaging. Other factors on radiographic noise, the big one is artifacts. And when we look at artifacts here, artifacts quite simply is nothing more than the misrepresentation of tissue structures on a radiograph. Now, back in the days of film, we're handling it with our fingers. We leave oil on the film. That can affect what is happening. If we accidentally bend the film, we create a crease or a crimp mark. That will distort the image. Scratching, it could be from our hands, our fingernails. It can be through the processing of our automatic film processor. And speaking of the processing, here we can have streaks, chemical streaks, where we're not properly squeegeeing the chemicals off the film. We can improperly dry it, leave water on there and have watermarks and spots, similar to what you would see in a dishwasher at your home. Again, scratches from rollers, scratches from our hands, dirt can destroy a piece of film, and also we can stain. Other factors that will influence noise, we talked about it earlier, was fog. This could be both chemical and safe light fog, creating a film's inability to accurately reproduce because it's already been a little bit pre-exposed. In our digital world, some artifacts that we need to look at today are burned out pixels. It could be dirt and grime on a detector when we change one out or have particles falling on it. These are things that we need to be very careful of when looking at radiographic noise. We've just finished looking at image quality. We've looked at both the sharpness and the noise, and we've discussed various factors. Now let's take a look at the components that make up the imaging chain. We're going to do this from both a radiographic and a fluoroscopic area. In the radiographic world, we have the X-ray tube, a beam limiting device or collimator. We have filters. We use ion chambers, bucking grids, and lastly, image receptors. In the fluoroscopic world, we've gone through a lot of changes and stuff. In the analog world, we had the X-ray tube, we have a beam limiting device, we have an II, which is an image intensifier, a light detector, a beam splitter, camera, and viewing devices. All right. Moving on into the analog digital world, kind of a hybrid area, you can see there's areas that are starred, the light detector, beam splitter, iris, and camera, and that would be determined, do you have more of an analog or a digital system? Moving into our digital world, you can see we've reduced some of the components necessary here in the fluoroscopic world in order to create digital imaging. But enough about the components. The bigger thing is this is what we're going to be focusing on because this is what we're going to be affecting when we talk about the service tests on the imaging chain. Now you can see a list here of 10 items that we're going to be discussing. I'm not going to rattle them all off at you. What I'm going to do is I'm going to jump right in and start with KV accuracy. When we look at KV accuracy, it applies to both modes, both radiographic and fluoroscopic. In the radiographic mode, we used a fixed KV during our X-ray exam. Why? It's limited to a maximum of 5 seconds by law. In the fluoroscopic area, it's a self-adjusting, and this is based on the output. What area of the body are we going over? The reason we have this self-adjusting is because by law this is limited to a 5-minute exam. However, KV is KV is KV. Whether it's radiographic or fluoroscopic, it is still KV, and we can measure it. In measuring KV, we measure it one of two ways. We either measure it invasively or non-invasively. Invasively means I'm putting a high voltage divider, making it part of the circuit, and I'm going to hook up a scope or a digital multimeter into my voltage divider network and measure the KV that is representative of it. In doing so, these dividers were either 100K, 10K, or 1K to 1 ratio, which would determine what you were seeing. As technology came over, and back in right around 1975, Keithley became the first non-invasive. Well, now there's a whole bunch of non-invasive companies out there making meters for us to do our job. Non-invasive is our most common today. What we do is we put a probe in the beam, and once we expose that probe, the mathematical algorithms then compute and give us our KV, and this is how we set up our machines for accuracy and also verify it. Now, the accuracy of the KV and the quality of the KV is influenced by the type of generator on the system. Early X-ray was single phase, half wave. Then we moved on to full wave. We moved on to full wave 6 pulse, full wave 12 pulse, and more recently and most common today are high frequency generators. The accuracy that we're verifying and checking is that the tolerance is generally plus or minus 1% from what the operator wants. As KV is considered the quality factor of the Q factors of X-ray, what we're talking about is the beam's ability to penetrate the object being X-rayed. This is something that we should accurately and ensure is spot on. Moving here from this, let's talk about MA and mass. In the radiographic mode, most of our generators today are mass generators. And what we say is mass is equal to mass. However, we need to recognize that mass is an algebraic expression of MA times time. MA and time have an inverse relationship, but this is still referring to the quantity of radiation. Now, when I say quantity, we're talking how much. Because mass is equal to mass, if I were to make an X-ray at 300 MA at 1 second, or if I made an X-ray at 150 MA for 2 seconds, both multiplication factors is 300 mass. The quantity of radiation is exactly the same. However, our machine responded differently, and we need to be sensitive to this because sometimes operators don't recognize that. Now, what can we do? We ensure that the filaments are accurately calibrated. In calibrating the filaments, we need to recognize that the filament circuits have got two forms of regulation. We have a standby and boost mode when we're actually controlling the voltages to the filament, and we're controlling what's happening, and we are regulating this. In standby, we keep them warmed over, and when we boost them, we apply higher voltage and more current through them to create the cloud of electrons as known as space charge. When we apply KV to the X-ray tube, that cloud of electrons dissipates. And now what we're concerned about is MA. We're concerned about the amount of current going through the X-ray tube. Here's where your waveform calibration is very important. What I recommend you use is a 3-point technique so that you can verify that your MA is at the appropriate level. That's because you can control the amount of time. In making these output waveforms accurate, what you're doing is you're extending the useful life of the tube. Now, this will have impact on other functions, so this is something we need to be very cognizant of. With this over here, we need to ensure that this is accurate because in manual mode, the operator is deciding what level of output that they want. When we use automatic exposure control or have a mass generator, we're letting the machine do that. So we need to ensure that this is accurate in order to create good quality radiographs. Moving on and looking at the fluoroscopic mode, this is much different. Because this is a longer exam, fluoroscopic is a low fixed MA output. It's maximized at 10 MA. However, output is typically between 1.5 and 6.5 MA output maximum in the fluoro mode. Value layer is a very important check that we need to do, particularly in the radiographic area. What half value layer does, it identifies the change in inherent filtration as your tube ages. We know from earlier discussion that inherent filtration is anything that is built into the tube that we can't get away from. Typically on a new tube, this is somewhere around 2.5 millimeters of aluminum, which is how we measure this. As our tube ages and we utilize our tube, the inherent filtration is going to change. This comes from tungsten particles from our filaments. As we utilize our tube, these boil off and they fall, either in the focusing cup or onto the glass port. But also when we're generating X-rays and we accelerate the electrons into the anode, we are hitting that anode with such force that we're going to be depositing the anode material also on the glass port. Now that's changing the inherent filtration, because as we've created the X-ray, now it's going through these tungsten particles or molybdenum particles that are now laying on the glass, which is going to change or harden our beam because we absorb some of the lower levels of radiation. All right, with this can impact what's happening with our X-ray tube. As I stated earlier, this predominantly applies to radiographic exposures, but it is something that we need to be aware of. Now, when we're talking about half value layer, what we're doing is we're taking pieces of aluminum and we're putting them into the beam and we're measuring how much aluminum is needed to cut the output radiation in half. This is what half value layer is, and some manufacturers will use this in the calculation of dose. All right? When we're looking at patient dose can be expressed as either millirads or milligrays per mass. Manufacturers that use this will generally use a lookup table. They will identify specific KVs, and its result is the output per mass. For example, if a manufacturer selected 28 kV and 32 kVs as their lookup table, and we made an X-ray at 30 kV, the MR per mass would be the mid-range point using the linearity application of radiation. As our tube output changes due to age, this is a table that we would then have to continuously update to ensure what the patient is getting in terms of radiation. Speaking of radiation and radiation dose, let's talk about dose. All right? Here in the radiographic world, this is kind of critical. All right? In the analog world, this is critical because we're trying to achieve a particular optical density, because film doesn't change. You got one shot at it, and we got to ensure that the radiologist can read that radiograph. In the digital world, yes, we're still concerned about dose. However, we have a little bit more flexibility in this because we can adjust the image a little bit using software for our eyes to see. In the fluoral world, we're not concerned about that quick little hard-hitting factor. We're concerned about maximum radiation over a period of time. So we're concerned about maximum R output, and every manufacturer has their own standard. You'll need to consult your book and you will set for the max R output. Typically we measure this 30 centimeters from the input to the II. This is considered the patient entrance dose. And this is going to be expressed as a dose rate, which is how much millirankins or milligrays per second. Some manufacturers use 70 kV for calibration of this area. Others will use something different. Consult your manufacturer's specifications for this. However, recognize that fluoro kV exists over the range from 40 to 110. Another area that we do testing on are beam limiting devices and collimators. All right? One of the biggest things that we can do to limit scatter radiation and help image quality is to ensure the alignment of the X-ray and light fields. The key thing here is X-ray is permanent. We need to address the light fields and make them representative of the X-ray field, not vice versa. The light fields need to be representative of the X-ray field because this is how the operators position their patient. By limiting the area we expose, we reduce scatter radiation. Another thing that we can do here is ensure the setting of the SID. We say this because the most effective tool we have in cleaning up scatter is a grid. Grids, as you know, can be linear or focused. They can also be crosshatch and crosshatch focused. The focus grids, though, have a specific operating range. So if we don't have a properly calibrated source to image distance, we can inadvertently affect the quality of our radiograph by having too much cutoff, thereby reducing good contrast. All right. The other thing this does, it also ensures proper operation and alignment of the positive beam limitation or automatic collimation size and sensing system, ACSS. Now, when we look at apertures here, apertures are fixed limiting devices. Back in earlier days, we used cones and cylinders. However, today, they're not used as much, except predominantly in dental X-ray. Collimators, which are variable apertures, also house extra filtration that is used. Typically, this is between 0 and 0.3 millimeters of material that can be added to the beam to shape the quality of the radiation we send to the patient. This is predominantly used more in video and in fluoroscopy. However, there are some radiographic applications. When we look at the collimators themselves in radiography, typically they have 4 blades, longitudinal and horizontal. A lot of manufacturers will have 2 motors. However, some have 1 motor for each blade or 4 motors in the collimator. In fluoroscopy, it's kind of an extension of the radiographic collimator. However, we're going to add some extra blades because we need an 8-sided hexagonal iris mode. All right, what this is going to do is this is going to shape the output of the X-ray beam to more match the round image intensifier and the appropriate field needed. A full field shot in some cases can be 40 centimeters, covering the entire bottom of the image intensifier. When we use zoom views, we restrict what we're trying to see, but we're still covering the image intensifiers. Hence, this is called zoom 1, zoom 2, or zoom 3 as appropriate, or mag mode. Moving on from here, automatic exposure control, AEC. Very important today because this ensures consistent radiographs regardless of the KV. Back in the days of film, this was critical. Doctors typically wanted an optical density of somewhere between 1.7 to 1.85 OD, and this varied from facility to facility. Our job was to set it up and ensure that that was there. When we did this, we calibrated all this at the normal density. Through normal steps, we could then change the amount of density on the exposure control using the density control in various steps, either plus or minus from the normal. In mammography, typically there was an 11 to 13% change, either brighter or darker, in the image quality based on whether we went plus or minus. In radiographic systems, a full step change can be anywhere from 20 to 25% change. Now, there are certain manufacturers out there that also do half steps. Again, we need to be cognizant of the type of system we have when we're checking and verifying the operation of this. Operation of AEC is accomplished differently by manufacturers. In radiography and a lot of manufacturers, photo timing or use of ion chambers is predominantly the one. However, there are some manufacturers out there that actually use calculated AEC. Basically what this means is they will take a sample shot at a particular time base, figure out how much radiation was received during that time, The internal calculations of the microprocessor will determine the amount of time, and then it will then continue the X-ray for that time based on a calculated base rather than live radiation. As we're looking at this here, and we're looking at dose, and what we're looking at here, the AEC we're trying to terminate based on mass or dose of what the patient needs. So if we look at how we calculate this, an example given here of 7.5 milliroentgens per mass, if I make a 200 mass shot, I'm looking at 1,500 milliroentgen dose for that one particular X-ray. As dose and mass are what's used to terminate AEC, we need to ensure that the proper level is set for this. CR, we've used the appropriate level of dose to set the S-curve that's required by the appropriate processor. Again, as I stated, and generally more accepted, this was critical in film radiography because there was no adjusting film, and we only had one shot at it. Like, right? Great. Otherwise, we had a double exposed to patient. While with dose is still important in our digital world, we do have the means to self-adjust it using the software, and therefore we can still get a good quality radiograph and have less retakes. Now, looking at this in the fluoro world here, as we get into fluoroscopy, we're going to look at some other things that we use to control our quality of our image. These are PMTs and PDAs that are used in fluoro. Another term that's going to be very important to you that you may see that affects the output of these devices is MTF, which is known as modulation transfer function. This is the image intensifier's ability to convert X-ray energy to light energy. Now, we've got the light spread across the bottom of this image intensifier, 40 centimeters. What we're going to do is take the output of the image intensifier, which is small. It's the same image, but now it's intensified. It's glowing much brighter. This is what the photomultiplier tube, PMT, or photodiode array, PDA, is reading. What they're doing is they're looking at the output of this. When we look at the output, if it is not correct, it's going to be part of the auto KV circuit, and it's going to adjust the KV, which is controlling the amount of penetration of the X-ray, and going to affect how much image we see in the X-ray field. This is how we ensure consistent brightness of our X-ray image during the live exam as the doctor rotates the device over our patient. Now, an II is a tube, and its output is going to degrade over time. So typically, this is a power supply issue. Now, IIs are sent today with a certification, and we should ensure that the appropriate voltages for the II tube are set for the acceleration plates inside this device to ensure we're getting the proper output set up. This is something we should verify on the PMs. And in the old days, while we were looking at high voltage, some of our modern systems today use a voltage divider network that is more representative of this. Camera irises and cameras. Starting with the camera iris here, what we're going to use this for is to control the light beam on the type of camera pickup device that's being used. Now, this isn't something that constantly changes throughout. It's going to be set based on type of dose that's going to be given, and it's going to respond at an appropriate level. All right? This responds based on the amount of light being emitted by the II and being sensed by the photomultiplier tube or PDA type of device. Now, some manufacturers have integrated the camera iris into the auto KV and regulation. Others haven't. Again, you need to consult your manufacturer's procedures for this. Looking at our cameras, typical device used are camera tubes and CCD cameras for picking up the light in order to create our images. Some service concerns that we need to be aware of is tubes age. How we compensate for this is by ensuring that the power supplies are proper, but also by adjusting the grid voltage, which affects the conduction of our camera tube. We can also ensure that the gain circuits are maximized to ensure that we get the proper output. When looking at CCD cameras, because it's a different form of technology, there are some manufacturers out there that are concerned about operating temperatures. I know one of the manufacturers that I've worked for, their CCD cameras have to be at minus 23 degrees centigrade in order to ensure maximum output of the image. In fact, there was a 10-minute wait that prevented images from this happening. Again, different manufacturers use them in different ways. You need to consult your book. One of the things about CCD cameras, though, is pixel burnout. If they burn out, there's no repair of them. The other thing that we have to be aware of with CCD cameras are the computer files available, such as white and dark fields. Now, as our cameras age, outputs change. We may have to adjust our white fields periodically to compensate for the age of our CCD cameras. And the other thing that we need to be aware of is defect maps to ensure that we have the appropriate one for the appropriate camera in our system. Looking at resolution here, this requires the use of a special phantom. The line pair phantom is the one that's most commonly used. However, some manufacturers will use a fine mesh screen. The purpose of this is to determine the quality of the image process based on how many line pairs or screen lines can be clearly seen. In using this phantom, back in the days of film, it really didn't make that much difference. However, when we look at fluoro, and when we look in today's digital world, it does make a difference. So typically we set this device at a 45-degree angle. On an II system, this is done so that the lines on the line pair phantom do not become part of the vertical and horizontal scans on the monitor or camera. On a digital system, we do this so that it's clearly distinguishable from the vertical and horizontal pixel rows in the event of outages or things of this nature, so we can clearly distinguish what is our line pair phantom. And moving on to our last area of viewing and recording devices, some information we need to look at on a video signal is we use a composite signal. This consists of the B or video signal, the A is the black, and the S is the sync. Resolution on our video signal is typically a high resolution signal. However, a lot of our recording devices use a low resolution, so we need compensation based on the various devices in the chain. In doing all this video imaging and processing and stuff, we go from our pickup tube or our camera or whatever device that we're using, and we send it to a computer who does all of this video processing. What the computer does is it stores information on the hard drive, and then upon need, it disperses it to the appropriate networks. In looking at these viewing and recording devices, let's take a look at some monitors, printers, and processors and things that we can be concerned about. One of our primary concerns is that of brightness. Do we have the minimum contrast resolution? Typically, what manufacturers use is the SMPTE patterns test. SMPTE standing for the Society of Motion Picture and Television Engineers. While this was predominantly designed as a printing test, we utilize these for various testing and viewing of lines and different shadow patterns to ensure the maximum brightness and clarity of our monitors. When we look at calibration, monitors, printers, and processors all have different calibration requirements. Our job as field engineers is to ensure that the output is maximized in the areas of our concern to ensure that we get the best quality image possible. When we look at pixelization, if we take a look at a camera, all right, more pixels, more data, more storage space required. Does that affect our image? Absolutely. When we look at monitors, this is modality dependent. It's also a difference between a technician and doctor's viewing stations. These all have to be calibrated differently. There are different requirements for each. We need to ensure that we appropriately have the right monitor, the right requirement for the appropriate area. Looking at some recording devices that are used today, we used to use VCRs. Well, those have all been replaced by technology, by DVRs today. However, depending on which one they got, These are both resolution devices, and so our output from our computer must meet this requirement. Another form of viewing that is associated more with film is that of cine. Back in the days of cine, this was a motion picture of a fluoroscopic exam. This previously used a big, huge roll of film, and we had a variable frame rate of 30, 60, or 120 frames per second were the most common ones found. Here, we were giving a higher level of radiation to a patient in order to record this. We used the output of the II. The output was sent to a beam splitter device, which was used to expose the film, and this was more common on older systems. Today's day and age, we use something called digital pulse fluoroscopy. Here, our MA output is somewhat higher than normal fluoro. All right? This creates an increased radiation to the patient, but this is also based on the number of pulses per second. This is used for special recording devices, but it overall results in a lower dose to the patient than a radiograph. Again, this is KV adjustable and will affect the quality of our image. Spot film devices, this was our old electromechanical nightmare. All right, back in the day, we had all these different possible multiple images per film. Again, this varied from manufacturer to manufacturer, but it was our job to ensure that we could distinguish between each of these images. Now, when we had these spot film devices, these actually changed the operation of our machine from fluoroscopy to radiography, and which was used to temporarily make an image of what the physician saw during the exam. So what we were doing is we were going from a maximum of 10 MA to radiography, which is a higher level MA, and again, this is based on the size of your machine, but because these radiographs needed to be perfect, every one of them were photo timed, hence the need for perfect photo timing calibration earlier on. In our digital world today, much different. We still have multiple image captures, however, all we're doing is capturing what the physician sees during the fluoroscopic exam. We're not changing the operation, we just temporarily make a capture and we're using that same fluoroscopic image. Our last area of discussion today is preventive maintenance. We can look at frequency, our specification sheet, meaning, and where it's used. Starting with frequency, basically, and typically these are twice a year. This is most manufacturers' recommendation. Minimally though, because of contracts and stuff, they should be done at least once a year. Some modalities actually require an annual physicist visit. Your PM visit should coincide with this visit. Our goal should be no errors from the physicist. Specification sheets, how important are they to us? They talk about the manufacturing and performance requirements, the tolerances, the minimums, the maximum, and ranges in some cases. It also provides guidance for us, how to do something, where to do something. Are there formulas needed in the compilation of our data? And where do we find it? In system manuals and also QC manuals. What does this mean to us? It means that when we sign off on a PM, you have verified and you have certified that the system functions are all performing according to specifications contained in the system's manuals. Here's a Johnism for you. If you get called back for an image quality issue, not a broken machine, within a day or two after you did a PMI, how good was your PMI? Where do these get used? They get used to satisfy inspection requirements for JACO, the ACR, and state. They also may impact reimbursements in some cases. It may affect a facility's ability to perform exams. This is modality dependent. For example, in the world of mammography, if they don't have an annual physicist visit documented and proven, they can be shut down from performing mammogram exams. So what did we cover today? We talked about image quality and the imaging chain from a service perspective. We talked about image quality itself. What does it mean? We talked about the imaging chain components. We talked about service tests that you do that affect the imaging chain. And lastly, we talked briefly about preventive maintenance. Any comments, questions, observations, or concerns from your end before I throw some out at you?
Thank you so much, John. Fantastic presentation. Lots of good information. We do have some great questions here. We're going to go ahead and get started. First question, why is there a difference when measuring dose between a radiography and fluoroscopy?
Well, basically, there's two different types of exams that are going on, and because of the way we calculate, we have to ensure what's being measured because we are very concerned about what patients are being exposed to. As we know, radiation is something that lasts a lifetime and is cumulative in nature because only 90% of what we receive is corrected by our bodies in 90 days. The rest of it just stays with us. And just walking outside, we get exposed to radiation. So we need to be very concerned about what we're exposing our patients to during diagnosis, but treatment is a different world.
Okay, next question. In your opinion, why is it we need to have an understanding of film-based systems in order to better understand our modern digital systems?
Because digital evolved from film. Film, basically, we had one shot at doing things. In our digital world, it is less critical. We have greater controls as operators, and we have machines helping us do things. We only had one piece of film that we either had to copy or one shot to get it right. If it wasn't right, we had to re-expose the patient. Our digital world, we have the tolerance, but all of the same influences affect both the analog world and the digital world. And a better understanding of the analog world makes us appreciate what's going on here in our digital world so much more and how the machines have helped us today.
Fantastic. Next one. In your opinion, what is the most important aspect of image quality?
Most important? Real simple. What does the doctor want to see? If we don't satisfy him, we're going to be back every day. Our job is not what we see, it's what he sees. What does he or she want, and what can we do to satisfy him in order for him to properly diagnose the patient and to ensure proper treatment of our patients and through patient care.
Okay, we're going to now start taking some of the questions from the attendees. The first one, regarding the image receptor for use in cath labs or high-resolution procedures, is there a superior image over II tubes over digital IRs?
From my experience and talking also with people that spend time in the cath labs, who have a lot more experience than me, the digital image today gives us a lot more flexibility. However, there is some compromises in today's digital image because we don't have the specifications quite as tight as they needed to be back in our earlier days of the analog world with the image intensifier and other factors. There are significant advantages in our digital world that didn't exist back in the other days, and so each of these is a compromise in their own way.
All right, next question. You have to forgive me. I am not a technical person, but it says, can you explain MGY again?
MGY is milligrays. All that is, it's a different standard from millirads. It's the amount of radiation. Milligrays are a typical standard used in the international area. MR is a typical standard used here in the U.S.
Thank you. Next one. What disadvantages have you observed with hospital IT personnel handling the PAC systems as opposed to an imaging specialist biomedical technicians?
Boy, that's opening up a whole can of worms over there. Basically, IT people see a computer and they want their hands on it. And oversimple, that's what a PACS is. It's a great big computer in its own way. It's just a storage device. The problem with that is not so much for us as much as it is determined by the laws of our country. The lawmakers have decided a computer that is attached to a medical device is to be serviced by trained modality type people, whether it's attached to lab equipment, imaging equipment, or whatever. It belongs to that particular modality and not the IT personnel. The IT personnel are responsible for providing the infrastructure network of the Ethernet where we can transfer the images across the, but it's up to us to maintain all of the hardware.
Okay. Next question. Many Siemens devices have 24-month PMI cycles. Do you have an opinion on that?
Again, as technology has taken over, devices have become more and more reliable. I remember back in the day we used to do semi-annual PMs, and in some cases we were doing quarterly PMs on equipment. As electronics and our technology has advanced, they've extended the life of the cycles. In addition to this, it's just what a manufacturer recommends because every machine is manufactured differently. They understand their tolerances of the manufacturing process, what they're putting together, and I'm going to defer to the engineers who do the design work. My job is to ensure that I'm meeting their specifications, not putting them together.
Next one. Can you please explain the section PDA/PMT once again?
Okay. A PMT is a photomultiplier tube. A PDA is a photodiode device. Both of these measure light intensity. They basically do the same function. It's just different levels of technology, one being tube technology, one being more modern electronic technology.
Okay, looks like we have one more question. What is the frequency of calibration? Is it the same as PM frequency?
Well, basically, if you think about it from my standpoint, and this is strictly my opinion, if I'm in there doing a PM and I'm certifying and verifying the operation, if I find something that's slightly off, I'm going to tweak it. So in that regard, in the way our technology also has evolved, because of our reliability, to me, calibration and PMI are one and the same. Years ago, when our tolerances were much greater due to older technology, there was differences in terms of PM, which was more of a operational check, and then a calibration, which was more of a detailed voltage tweaking type check. Today, they're one and the same.
Excellent. Okay. Thank you so much, John. And let's thank again our today's sponsor, Technical Prospects. One lucky attendee will win lunch for their whole department. Details are included in the post-webinar survey, which will appear on your screen shortly. You must complete the survey to obtain your certificate of attendance. If you do not see the survey, you can email us at webinar@mdpublishing.com. Thank you again to John and Technical Prospects. We appreciate you coming to another excellent webinar Wednesday. You guys have a great rest of the day.
Thank you. Thank you.